Now, last time we talked about polar coordinates, and we're going to continue that today. In fact, that's sort of the last big thing, is polar coordinates. So what are polar coordinates? Well, the idea is we're going to just change the way that we describe points. So instead of describing points as x and y, we're going to describe them as r and theta. So where theta is the direction that we go, and r is a distance, how far out we need to go. So today we want to talk about a couple of ideas, and the first thing we're going to talk about is sketching. So we want to talk about how do we draw these curves. And when we are in polar coordinates, we almost always think of r as being a function of theta. So given a direction, how far out do I need to go? So that's what we want to do. And we saw a few simple examples last time when we sort of were doing the switching back and forth between the polar coordinates and the Cartesian coordinates. So how do we go about doing it? Well, if we were a computer, the way a computer does this is it says, I'm going to plot a lot of points. I'll plot 100, maybe 1,000, maybe 10,000. Just depends on how much time I have and how much precision I want to do. And then once I have all these points, I just connect the dots. Now, that's if you have a lot of patience and you'll have a lot of time. If you don't, we do what we would do in calculus, which is say, look, not all points are equally important. So instead of trying to plot all the points, let's identify important points. Now, you might say, well, what makes a point important? Well, important points tend to be 0. That's when you're at the center, the origin. And also where you're as far away from the origin as you can be. So in some sense, the maximums and minimums. This is the same sort of idea that we had when we talked about curve sketching. It says, look, let's not draw every point. Let's draw a handful of points, and then we'll connect the dots there, because we can understand what's happening in that setting. Now, you can look for symmetry. It doesn't need to be done, but we'll just point out, we're symmetric across the x-axis, so if we think of this as our coordinate system, and we've drawn it in a different way, you'll notice it's not these square lines that we're used to. Instead, there's this central point, and we have these circles. And the circles represent different values of r, how far out we go. And then there's these rays, and they represent different angles. So we say we're symmetric across the x-axis, which means we have that type of symmetry. Well, that's the case if I plug in the negative theta, it's the same as if I plug in the positive theta. Well, why is that? Well, if you think of the picture here, if this is theta, negative theta goes directly across the x-axis. So it's saying in both cases, you go the same distance out. So if you go the same distance out, then you're going to have that symmetry showing up. You're symmetric across the y-axis. In other words, we have this type of symmetry where we can fold it over. Well, that would happen is if f of pi minus theta is equal to f of theta. Now, why is that? Well, you just think about the relationship between the angles pi minus theta and theta. And if you think about it, theta goes in this direction. Pi minus theta says go pi, but then go back theta. So it's over here. And you see that these two angles are the angles which are directly across the y-axis. So we won't generally look for symmetry, but that's something you can be aware of. All right, so now we're going to start by sketching the curve r equals 1 minus cosine theta. And we'll just identify any symmetry. So we can identify symmetry at the end by looking at the picture. We can try to identify symmetry at the beginning by saying, well, what type of symmetry do we have? Do we see any obvious candidates for symmetry that we should expect? Well, the only place where theta shows up is here. What do we know about the cosine function? The sinusoidal, which means it looks like the sine function. Is it odd or even? It's an even function. And so that says if you plug in negative theta, it's the same thing as if you plug in positive theta. So it will be symmetric across the x-axis. So how do we do this? Well, what I recommend is we start with where we're comfortable. The place where we're comfortable is trying to plot things if we think of it back as like y is a function of x. So I'm going to do that. So what I'm going to do is I'm going to make a little grid here. And here I'll put theta. I'm thinking that's my input. And here is r. Now this is not the polar curve I'm plotting. I'm just trying to say, let me think of r as a function of theta, and what would it look like? Now if you think of r as a function of theta, well, of course, one thing we should know is where does theta go between? If we say r equals 1 minus cosine theta, which values of theta should we use? Okay, we have a candidate, 0 to 2 pi. That's a great answer. Now, another answer is we can say, we'll use all the values of theta. Why not? Well, it's true, we can, because there's no restriction on theta. A priori, if we're just given a relationship, we say, look, theta can be arbitrary. So why do we say, well, let's just look between 0 and 2 pi? What's special about this function that allows us to say, if you just go between 0 and 2 pi, that's good enough? It's going to repeat. Yeah, that's the important idea. This is a periodic function. And so whatever the behavior is between 0 and 2 pi, it's going to be a similar behavior every 2 pi interval thereafter. So once we have one interval, that's good enough. Okay, r equals 1 minus cosine theta. Well, where is it at theta equals 0? It's at 0. Now, what happens after that? Well, what's true? Well, we got to think about this. Let's think about the cosine function. What's the largest cosine can get? 1. Where does that happen? And 0 and 2 pi. So the largest this can ever be is 1. So that says the smallest r can ever be is 0, because 1 minus 1. And that happens at 0. And again, it happens at 2 pi. What's the largest cosine theta can be? Yeah, sorry, we already answered that. What's the smallest it can be? -1, right? Okay, so where does cosine theta equal -1? At pi. And so if I subtract 1 minus -1, that's going to get us all the way up to 2. Okay, we're almost there. In fact, we know a little bit about the cosine function. So what's going to end up happening here is it's going to come up, and then it's going to come down. So the idea is we know the extreme values, and we just sort of connect the dots to some extent. Now we can actually plug in some more information. For instance, at pi halves, what will happen to 1 minus cosine of pi halves? What will that be? Yeah, cosine of pi halves is 0, so we'll end up with 1 minus 0. So we'll end up with 1. How about at 3 pi halves? What will we get? We'll end up with cosine is 0, and so we'll end up with a total value of 1. Okay, so there's some values. Now, this is not our picture, but we're getting close. Now what we're going to do is we're going to come and plot things in our plane. So let's start with the key points. We know at the angle 0, which is this angle, we are at the value of 0, so we're going to start there. And then, by the time we get to pi halves, which is going straight up, because we come around up to pi halves, we're going to go out to distance 1. Well, let's say this is distance 1 here. At pi, we're going to go out to distance 2. So that would be roughly here. At 3 pi halves, we're going to go distance 1. And then at 2 pi, we're back to 0 again. All right, so those are sort of, we plot the key points. And now we just sort of say, okay, what's happening? Well, we think about as we change our angle of theta, we either are getting further away or closer. So we're just going to start here and say, where are we getting further away from the origin? what interval? 0 to pi, because that's where our function goes up. So what happens is we start here and we increase. So we look something like that. Where do we get closer? Pi to 2 pi, because that's decreasing. So where r is decreasing, we're going to get closer. So now we start to get closer until we come back around. And that's our curve r equals 1 minus cosine theta. Now, if you turn it sideways, you can see that it has a particular shape. This is sometimes called a cardioid, because it vaguely resembles what people might draw for a heart shape. So, all right, good. One example down. Let's try a couple more. And we'll get pretty good at this. So, next one. Sketch the curve r equals 4 sine of 3 theta, and we'll identify any symmetry. Okay, so let's just sort of walk through our process. And we say, well, how often will we repeat? What's our interval? So it's still going to be 2 pi. So, all right, so I'm going to come here, go up to 2 pi. Now, 4 sine of 3 theta, the 4, that just says we're going to go out to distance 4. That's okay. That just means we go higher and lower. What does the 3 theta do? What's the effect of that? Sorry, what? Increases the frequency, right. Okay. So what's going to happen is normally, if you think about sine, it would just go up and down and back up one time. Sine of 3 theta will go up and down how many times? 3. All right. So we should split this into roughly thirds. So we're going to go up and down and up and down and up and down and up. So this is what the curve r equals 4 sine theta, 3 theta would look like if we were thinking about graphing it in the sort of a theta r plane like we would a Cartesian. We got to translate this now into polar. Now in some sense what's happening is when we have this, really what we're doing is we're taking this shape and we're somehow bending it around. I know that's very vague, but we're imagining that this part right here, that's r equals 0, that should be the origin. And so we're somehow compressing that down and as we swing things around. All right, so we need to identify key points. Well, let's talk about the zeros. Where do we have zeros at? Pi over 3? Okay, let's see. I think that one would be here. I hope. Okay, where else? Two pi over 3. And? Pi. Okay. Also known as 3 pi over 3. And then? 4 pi over 3. Okay, we've got one more. Okay, 5 pi over 3. All right, so those are when we're going to hit the origin. All right, so pi over 3, well, that would be about 60 degrees. Let's see if we can figure this out. How many? 1, 2, 3, 4, 5, 6. I think that means we need to go every 4. So 1, 2, 3, 4. So that should be 60 degrees there. 1, 2, 3, 1, 2, 3, 4. Yep, that should be the next one. So I'm just marking my zeros. 1, 2, 3, 4. There we go. 1, 2, 3, 4. 1, 2, 3, 4. Okay. So these lines that I've drawn are at these angles: pi thirds, 2 pi thirds, pi, 4 pi thirds, and 5 pi thirds and 2 pi. Now, The next thing is let's talk about where are we at the peaks. So this is at 4. So where does this one occur? Pi over 6. And so it's out at distance 4, so I'm going to go out to pi over 6. 1, 2, 3, 4. Okay, so there we go. There's a point. Now, where's this point at? So I need to be halfway between pi over 3 and 2 pi over 3, and that's pi over 2. How far do I need to go? What's the value for r? -4. So remember, I need to face a direction and go a distance. So here when we went in the direction pi 6, we went 4. Now, when I'm looking in the direction pi over 2, I need to go -4, which means I need to walk it back. So it's 1, 2, 3, 4. So that's where I'll be at pi over 2. Okay, and all right. Well, the next point is going to be +4, and it's just going to alternate. So it's going to be out 4, back 4, out 4, and so forth and so on. So out 4, 1, 2, 3, 4. Then in this one, it's going to be halfway in between, and then we're going to go back 4, and what do you notice? We go back. Yeah, we actually hit that same point. Okay, then here, we're going to be at +4. We actually are going to hit that same point. And then here, we're going to go -4, and we'll get that back to that point. So those are the important points. Now, what does it look like? Well, we start at 0, and then we're going to go up. So we're going to come up to here. So that's the first stretch. Then we're going to go down. That's this next stretch. Now we're going negative. So normally in that interval for theta, we'd be up here, but because r is negative, we're down here. And so we're going to go down to -4, back up to 0. And now the next one, so we're up to this point now. Now we're going to go up to +4, then back to 0. So up to +4, back to 0. And we've now gone to this stage here. And at this point, what happens is we actually go and we end up looping around the same shape a second time. So this actually gets double covered. So that's the shape. That's the shape r = 4 sine 3 theta. So it turns out we actually didn't even need to go the whole 0 to 2 pi. We just needed to go 0 to pi. It's not so obvious that that happens beforehand. So it's good to go through and work out an example. Because of that, there are certain things that happen. We're going to get into that on Friday. You're going to be a little bit careful when it comes to finding things like how much area there is. That's what we're going to talk about on Friday. Does this have any symmetry? Yeah, it actually has this nice symmetry across the y-axis. So I don't think that's so obvious beforehand, but, well, it's true. Okay. R squared equals 4 sine of 2 theta. Well, all right. Let's see. So let's just first start by, let's just graph theta and r, and let's just graph 4 sine of 2 theta. We're not going to do r squared, we'll just do 4 sine of 2 theta. Okay, well, if we go up to 2 pi, the sine of 2 theta, over here we said we're going to repeat it 3 times. This says we'll repeat it twice. So we're going to go up and down, and up and down. Okay, so this is -4, +4. And it's not so hard to figure out because we split things into 4s. Here's pi halves, here's 3 pi halves. So this would be 4 sine of 2 theta. Now, if we sketch the next level, well, we'd really want to say, take the square root. R equals plus or minus 2 sine 2 theta, because that's what can happen. So we've got to be a little bit careful here, and here's our little bit careful. can r squared be here? We have r squared, which is 4 sine 2 theta. Would this work? No, because in this range for theta between pi halves and pi, sine of 2 theta is negative, so there will be nothing from here. Same thought process says there's going to be nothing from there. So we're not going to hit any of those points. But what we will hit is we can take this part, but now we take the square root, it's going to go just to 2. And of course we can also do the negative part because we can have r be negative. And then we also, between pi and 3 pi halves, and we have that negative part. So that's what we really want to sketch. So let's see, that's pi halves, there's pi, and there's 3 pi halves. All right, so what do we do? Well, we know the important points. So let's work with this first piece. So here, we're going from 0 up to pi halves. And this says you start, you move out, distance 2, and then you move back in. So that's our shape. Or, if we were to go negative, we could go out, distance 2 here, and then back inside. So that's our two possibilities in this range here. Now what about between pi and 3 pi halves? Well, if you're between pi and 3 pi halves, you're down here. So you would trace over this curve. Oh, it's actually the same curve. And over here, you trace over that curve. And so r squared equals 4 sine 2 theta. We have this almost a figure 8 turned slightly sideways. There's just nothing in here because of that r squared. All right. Now, you might be nervous and wondering, are we going to have to do a lot of drawing on this exam? And the answer is not a lot. Most of the time we give you the pictures. You might be expected to do things like match a picture with a function, but we know you're not trained artists. All right, any questions here? I'm sorry, I know I'm going kind of fast. All right. One more sketching problem. Sketch the region where 1 is less than or equal to r is less than or equal to 2 sine of 2 theta. All right, this should be a little bit easier, nothing crazy. First off, let's start with 1 is less than or equal to r. What does that r equal 1 look like? Circle of radius 1. So we can come and we can say, all right, circle of radius 1, well, let's put that here. So we have to be outside of this circle. That's the circle of radius 1. Notice that it says 1 less than or equal to r. That's another way of thinking of it as r is greater than or equal to 1, which means we're at least 1 away. So we're on the circle or farther out. Okay. All right. So now let's work on that 2 sine of 2 theta. So this will be very familiar. And because of that, I'm not going to spend a lot of time. We are going to go up and down and up and down. And we peak here at 2. We bottom out at negative 2. Our zeros are in very convenient location at pi halves, at pi, at 3 pi halves, and at 2 pi. So that tells us if we mark, okay, the directions where our zeros are at, these are our various directions here, pi halves to 3 pi halves, pi, 2 pi. So what does it say to do? Between 0 and pi halves, what are we going to look like? We're going to start at the origin, go out to distance 2, and come back. So some people might call this a leaf. So start at the origin, out to distance 2, and then back again. Between pi halves and pi, so now we're here, what are we going to do? Yeah, so we're going to go, same thing, we're going to go out, then come back in. But because r is negative, if r was positive, we'd come out into this piece, because this is where theta is between pi halves and pi. Because r is negative, we're going to come out down here. So we're going to come out, distance 2, and back in. Between pi and 3 pi halves, so that's this part, r is positive, so we're going to stay in this part. So we're going to come out to distance 2, and then we're going to go back in. And then finally, from 3 pi halves to 2 pi, which is down here, but r is negative, so we're actually going to shoot across to the other piece. So we're going to come out, which is, again, that's really negative 2 out, and then come back in. So that's our shape, kind of like a 4-leaf clover. So it's interesting that there's this sort of strange phenomenon when you have like a 2 theta, we're going to have 4 leaves, but when you had 3 theta, which we had a while back, there were 3 leaves, and what we did was we ran over them twice, and this tends to happen. Now, we want to be inside this curve, 2 sine of 2 theta. So we want to be outside the circle, but inside that curve. How many pieces do we shade? All right, I'll give you, this one is a freebie. That one will definitely be colored. So this is part of the region that satisfies that r is between 1 and 2 sine of 2 theta. Are there any others? Okay, so there are 3 other candidates, and it looks like we should shade them all. Maybe we do, or maybe we don't. What do you think? Do we shade all the other little pieces?
Well, the negative ones would be negative.
Yeah, this is where you have to be careful. So if you come up here and think about where 1 is in this picture, we really want to shade those parts, because those are places where r is between 1 and 2 sine of 2 theta. In these places, r is acting as a negative value. And I can't have that be bigger than 1. So it's sort of this counterintuitive thing. Just based on the picture, if we walked in without information, we said, oh, if we want the area between, we'd color all 4 of them. But because we have that information, we say, well, actually, we're going to cover just the parts where we had r was a positive value, because that's going to satisfy the right relationship. So here, we just have those 2 pieces get colored. All right, good. If I'm making you nervous about drawing, I do want to assure you, we will provide lots of pictures on the exam. This is not an art class. It's a math class. Yeah. Okay, so summary for drawing. The best way to draw is to get a quick sketch of what does it look like if I just think of r as being a function of theta, not in polar, but in rectangular coordinates. And just think about, okay, am I getting further out? Am I getting closer? Identify a few key angles, and you can mark some points. And you can get a pretty decent quick sketch. And oftentimes that's all you need. It's just enough to get some pretty decent information. And once you do a couple of these, it's not so bad. It goes pretty quickly. So we want to transition and talk about our second topic for today is tangent lines. Because we have curves, and one of our basic philosophies is like, well, if we have something that's a curve, maybe we can talk about tangent lines. And what do we mean by that? Well, if you came down here and you said, well, let's look at that part, and you were to zoom in, you would see it's looking something like that. And if you were to zoom in again, you would see that it's looking very straight. So in other words, as we keep zooming in, it looks flatter and flatter. It looks like a line. And in math, we love those lines. Those lines are giving us information. So we want to be able to talk about tangent lines. Now here's how we do it. What we do is we say, let's not reinvent the wheel. We have ways to find tangent lines to curves, and in particular, we have the notion of parametric curves. So currently, we can think of our r being a function of theta. So we can say, let's go back and write things in terms of x and y. And the reason why we want to do that is that lines work a lot better in rectangular coordinates. If you remember some of the examples we did last time where we had some relationship which turned into a line, it was not a very easy thing to work with. But in rectangular coordinates it is. So we want to somehow convert these curves into rectangular coordinates. The way we do that is to remember our basic facts. X is our cosine theta, and y is our sine theta. And if we have this curve, r equals f of theta, I can now say, well, the x value, that's f of theta cosine theta, and the y value is f of theta sine theta. And now we go back and say, okay, we have ways to find our slopes. Because the slope is always the hard part. The point, that's almost a given. You plug it in. For the slope, you take y prime over x prime. Because think of it, y prime is change in y. X prime, change in x. So change in y over change in x, that's your slope. So what do? Well, so you come to your function for y, and you use the product rule. The derivative of the first is f prime of theta times the second sine theta plus the first f of theta times the derivative of sine, which is cosine, divided by the derivative of x. Again, product rule. Derivative of the first, f prime of theta times the second cosine theta, and then the first, which is f of theta, times the derivative of cosine, which is negative sine. And that's it. And that's it. That's how you find your slope of your tangent line. And once you have your slope of your tangent line, then you're good to go. Because you have the point, life is good. All right. Let's try an example. Find the tangent line for the function r equals 1 minus cosine theta at theta equals pi over 2 and theta equals pi over 3. All right. So what do? Well, let's just walk through our process. We know that our x of theta is our function for r, so 1 minus cosine theta times cosine theta. So r cosine theta. And our y of theta, that's our function for r, 1 minus cosine theta, times our sine of theta. And we can multiply this out. We get cosine theta minus cosine squared theta. And here we get sine of theta minus cosine theta sine theta. Now, if we wanted, we could do various things. For instance, we could use power reduction to make things simpler to work with. Or if we're just like, who needs things to be simple? Full speed ahead. Well, all right. Full speed ahead. Here we go. So we're going to focus on the slope for a minute. So this is the part where I almost always screw up. And I'm saying that out loud, not because I expect you to screw up, but because if I say that, then I'll remember not to do it. Which is, we take y prime over x prime. But the thing that always throws me off is I always write the x first and the y second. So the mistake I keep doing over and over again is like, let me take the derivative of this, the x term divided by the derivative of the y term. No. You got to be careful here. So make sure you're taking the derivative of the right term in the right place. So we're going to take the derivative of the y term on the top. So start here. What's the derivative of sine of theta? Well, let's just start with that. Sine of theta. What's that derivative? Cosine theta. Derivative of cosine theta times sine theta. Well, that's product rule, derivative of cosine. Negative sine, so there's already negative, so that'll be a plus sine squared. And then come to the derivative of sine, cosine, and times that by negative cosine makes that a minus cosine squared. Divide that by the derivative of x prime. Well, derivative of cosine, negative sine. Derivative of minus cosine squared. Well, minus. The 2 comes down. Cosine theta to the first, and then what? Times the derivative of cosine, which is negative sine. That negative helps me change the sign out there. And so there's our derivative. All right. So now we have our formula to get our slopes. So let's start with these lines. So first do theta equals pi over 2. So first off, let's talk about our point x comma y, where this is at. So we plug in pi over 2 into here. 1 minus cosine pi over 2. It's 1 times cosine pi over 2. 0. So that says our x-coordinate is 0. 1 minus cosine pi over 2 is still 1. Sine of pi over 2? 1. So our point is at 0, comma 1. Our slope, so this is our point, and our slope, well, we are going to take y prime of pi over 2 over x prime of pi over 2. Now, the good news is anything that has a cosine is going to become a 0, because cosine of pi over 2 is 0. And anything that has a sine is going to become a 1. So we can do this really quickly. We see that's going to be a 0, a 1, and a 0. So upstairs we have a 1. And downstairs we have a minus 1, and then a 2, and a 0, and a 1. So minus 1, which equals minus 1. And that's our slope. So our point, 0, 1, our slope, negative 1. So actually, this is really nice. That says our y-intercept is at 1, and our slope is minus 1. So we get y equals minus x plus 1. So that's our line. Now we can actually check our answer, or at least see if we're close, because this curve, 1 minus cosine theta, isn't just any curve. We've seen it before. So where have we seen it? Well, it was our first example. So that would be that point right there. And it does hit at 1. And now we say, well, let's sketch the tangent line. Does it look like it has the slope of negative 1? Seems pretty good to me. Okay, good, good. Reasonable answer. Reasonable answer. Those are the best kind. Much better than the unreasonable answers. All right, let's try the other one. Okay, this one should be fun. Theta equals pi over 3. Okay, so our point, x, y. Well, let's just remind ourselves, what's cosine of pi over 3? And what's sine of pi over 3? Cosine pi over 3? Is a half. Sine of pi over 3? Square root of 3 over 2. So, if we look, we get 1 minus cosine, so that's going to be 1 minus a half, so it's a half, then times another half, so our x-coordinate is a fourth. Our y-coordinate, 1 minus a half, so that's a half, times square root of 3 halves. So that's going to be square root of 3 fourths. So there's our point. Now, our slope. This one, it's going to take a little bit of time. Maybe. All right, so let's work it through here. We've got the cosine, that's a half, plus the sine squared, which is square root of 3 halves squared, that's 3 fourths. Then we're going to do minus cosine squared, which is minus 1 fourth. And downstairs, minus the sine, so that's minus square root of 3 over 2, plus 2 times a half times square root of 3 over 2. What do we have upstairs? A half plus 3 fourths minus a fourth. What does that turn out to be? 1. What do we have downstairs? The 2's cancel there, so it's minus square root of 3 over 2 plus square root of 3 over 2, which is 0. Now, 1 over 0 means what? No! 0 over 0 means more work. What does 1 over 0 mean? It's a vertical line. Because what is happening here, you can see, the y prime says, yeah, y is changing, but x is not changing. So if your x value is staying still, but your y value can go up and down, the only way that can happen is if you're on a vertical line. So what does our tangent line become? Well, it's a vertical line, which means I'm just at the x value. So our line is x equals 1 fourth. That's the answer. Now if you come here, we can sort of see, were we close? Well, we should be roughly here, and that looks pretty much like a vertical line. So that's good. All right. We can do this stuff. All right, how much time do we have left? Oh, we have a few minutes left. Find all the tangent lines at the point where the polar curve r equals 4 minus 2 sine 1/3 theta intersects the positive y-axis. Now, we're going to be a little bit careful here, because this is the first time we've seen a third show up. What interval should we be looking over? Yeah, we need to look over from 0 all the way up to 6 pi. So it's going to be a while. Okay. All right. So r equals 4 minus 2 sine of 1/3 theta. So, well, the minus 2 just says we're going to flip the sign upside down. The 4 says we shift it up. So it's going to start here at 4. So this turns out to be at 4. And then it's just going to slowly move up and down. And this all the way over here is at 6 pi. So by 6 pi, we've come all the way back. Now, there's a few things that are working in our favor. The value for r is always going to be in between 2 and 6. And where that 2 and 6 is coming from is I have 4, and this other part, this sine of 1/3 theta, can be at most 1 or negative 1, which says I can go at most either up by 2 or down by 2. So that says I'm between 2 and 6. So this is going to be very, very helpful for us. Now, when are we going to hit the positive y-axis? In other words, when are we hitting this line? What's the choices for theta? So there's some which aren't so hard to figure out. For instance, what's that angle? That's pi over 2. Okay, and then, how about that angle? Yeah, it's an additional 2 pi. So it's pi halves plus an additional 2 pi, which makes that 5 pi over 2. And what about that angle? Yeah, now we go around 2 times around. That gets us up to 4 pi. 1 more pi over 2. That's up to 9 pi over 2. All right. So that's the times. Those are the values for theta where we're going to hit. All right. Good. Good. We're making progress. And, all right. Actually, I don't think that's 4. I think this might be 4. I'm not sure now. I'm unclear. One of these is 4. One of these is 4. Okay. Well, what's the next thing we need to do? Yeah, so one of the things we need to do is figure out where do we intersect. So the nice thing is that our points have the form 0, comma something, because we're hitting the positive y-axis. So to figure out what these are, we plug things in. So for instance, sine of pi over 6. Do we know what sine of pi over 6 is? I'm plugging in pi halves in. Sine of pi over 6 is a half. So we get 4 minus 2 times a half, which makes this 3. If we come to 5 pi over 2, 5 pi 6. Well, what's sine of 5 pi 6? Ooh. 5 pi 6 is still a half. Yeah, so it's still at 3. And now plug in 9 pi halves, 9 pi 6. Well, that's 3 pi halves. Sine of 3 pi halves is negative 1. So you get 4 minus 2 times negative 1, which makes us 6. So those are the points. What's the other thing you have to do? Well, the other thing you have to do is you set up your equations. You have your x of theta. That's your 4 minus 2 sine of 1/3 theta times cosine theta. Your y of theta, which is 4 minus 2 sine of 1/3 theta times sine of theta. R cosine, R sine. Find your y prime of theta over x prime of theta, whatever that turns out to be. Evaluate, and then give the line. Because we are actually done with time, so we'll just stop there. That's the process. That's the process. All right, come back next time, because we're going to do some fun stuff and finding areas in polar coordinates. So see you on Friday. Bye.